Hi everyone, this is class number 12 for Engineering 221, Engineering Economy. This recorded lecture is being posted in lieu of our normal class meeting that was supposed to be scheduled for Thursday, April 10th. I'm out of town at a meeting, and so this recorded lecture replaces that. If you happen to be watching this class meeting before Wednesday the 9th, please remember that homework 6 is due on Wednesday the 9th at 3 p.m. Also, we're going to be back to our normal time and place on Thursday, April 17th. We'll be back to our class location down in Gullickson Hall number 5. And also on that day, Thursday the 17th, is when your course project is due. Remember that the course project is an attempt for you to project into the future on what your revenues and your expenses are going to be throughout not only your career but also retirement. Please refer to the assignment description and let me know if you have any questions. I'd be more than happy to help you out with that assignment. Today we're going to be starting on Chapter 6, which is Comparison and Selection Among Alternatives. Chapter 6 continues many of the ideas that were introduced in Chapter 5, where we were just evaluating a single project and trying to determine a yes or no answer on a single project. Here in Chapter 6 we're going to be looking at several different alternatives for a certain need and then trying to figure out which one is best. At the end of the lecture, I'll work through in-class exercise number 10, which I'd also encourage you to work independently so that you can get some practice with some of these ideas. Within Chapter 6, the primary objective is to compare alternatives. And what we want to do is develop tools that we can use in order to have a rational and a grounded way to make comparisons of alternatives that we designate as mutually exclusive alternatives, or MEAs. Mutually exclusive is going to mean that only one of the options can be selected to satisfy the need that exists. We did a similar thing in chapters 4 and 5 when we were applying the present worth, future worth, and annual worth methods. And remember that the criteria for each of those was that when we discounted the cash flow to the present, future, or on an annual basis at the MAR, which was the minimum acceptable rate of return, if we had a positive net cash flow, then that meant that the project is justifiable. In the internal rate of return method and also the external rate of return method, what we were able to do was calculate the actual rate of return, and then presumably we could compare that against what we designate as our minimum acceptable rate of return. Now things are a bit different in Chapter 6 though, because we have more than one option available. You can't do every project. Sometimes it's because of limited money, and sometimes it's because you only need one piece of equipment to satisfy any given need. So take, for example, transportation. You're a college student. You need the ability to move around campus and also maybe between campus and some off-campus locations like food and housing and entertainment. And so you have a number of options available to you, and they're not necessarily mutually exclusive at the individual level. You might own both a bicycle and a car, although probably very few people at Marshall own a helicopter. But in terms of a business and companies, a mutually exclusive alternative is one where you're trying to do something very specific. And so if you are trying to deliver a package from your warehouse to a customer, then you couldn't deliver that package both by bicycle and by car and by helicopter. You couldn't deliver that one same package the same way. And so in choosing how you're going to deliver, you would have alternatives that are mutually exclusive. Now, typically when we have an investment alternative that we have to decide between, the different alternatives that are available to us are going to generate different returns. They're going to have different costs associated with them, and they'll have different useful lives. And so using the pictures on screen as an example, a bicycle is less costly than a car, but then it's less costly to purchase, less costly to operate, but then maybe you're not able to deliver goods as quickly or deliver them as far away from your point of origin. And so we're going to try and consider all of these different factors when we compare alternatives, and the key to doing that is to finding a quantitative and a numerical expression for every difference between the alternatives. In other words, trying to break it all down to money so that we can have a reliable and uniform comparison among the different options that are available to us. So the fundamental purpose of investment, the whole reason we're willing to make some cash outlay at the beginning of a project or when we purchase a piece of equipment for a business, is that we want to obtain a return. And remember that each business has some minimum acceptable rate of return. And we've talked about this a couple of times, that if a business is borrowing money from a bank, they don't want to borrow money from a bank and then generate less of a return than their borrowing costs. And at the same time, you wouldn't want to initiate a project in order to get a return that's less than you could have just put your money in the bank and got a return on. So your basic rule is, when you're applying these principles, is that you want to spend as little as possible unless any additional dollar can be justified. And so going back to the case of transportation, why would you ever spend more than the cost of a bicycle for a van and purchase a scooter? And just from a strictly economic standpoint, the only reason why you'd spend the extra amount is if the scooter somehow enabled you to obtain a greater return than the purchase of the bicycle did. So in other words, any amount that's spent above the minimum has to pay its own way and provide some sort of an economic advantage. So I looked up the prices of these two different transportation alternatives, and this bicycle is kind of a mid-range hybrid bicycle that's a hybrid between a road bike and a mountain bike, $420. Its brand is Giant. And there's a retro scooter made in China, so it's very inexpensive, $890. And so what would be the economic advantage of the scooter, where you're going to be paying an extra $470 compared to the bicycle? In engineering economy, what we'd want to do is we'd want to find out on a dollar-by-dollar basis how much that extra investment is going to lead to an extra income for a company. Now, in doing this, we have to always start with analyzing the base alternative. And oftentimes our base alternative, the first option that we consider, is doing nothing at all, just leaving things the way they are, because that's what's going to require the least capital. It's the investment. Doing nothing requires $0 in a lot of cases. Now, sometimes it's not an option. Sometimes you have to have a piece of equipment, but in any situation, whether do nothing is an option or isn't, the base alternative that you have to start with is whatever the least expensive alternative is. And we're going to face two different types of decisions in engineering economy. In one of the cases, we'll end up with investments that are going to generate a return. And so an investment alternative is one where you have to put down money at the beginning, but you're going to earn additional revenue in the future because of that initial investment. In this case, do nothing is usually an alternative that we have to at least consider. The way that we know whether we should do an investment alternative is if the sum of the positive cash flows is greater than the sum of the negative cash flows. That tells us the internal rate of return is going to be greater than 0. And if we have the internal rate of return greater than our MAR, we should do the project. Another attempt to comparing an investment alternative, whether we should do it, is remember that we can find the present value, the future value, or the annualized value of some cash flow diagram. And if we use the MAR to move the money to a single time period, and the positive the value in the present, future, or on an annual basis is greater than 0, then that means the investment is profitable. But if it is not greater than 0, then that tells us that do nothing is better. You wouldn't want to make an investment, and when you are trying to earn the MAR, if it's giving you a negative present value, for example, then you should just not make any investment at all. And so this is a review of the methods that we use to analyze a single project, and the same kind of idea can be applied to analyzing multiple projects. Is you can find the present value, future value, or the annualized value for a series of alternatives and then find out which one generates the most cash flow. The other kind of alternative that sometimes we'll face, and hopefully not too often, is the case where we have to pay money, but we don't really get any return from it. All the cash flows are negative in a cost alternative. There may be some small salvage value at the end of the project lifetime, if that's applicable, but ordinarily these are must-do situations, and so the do-nothing approach is not an option. And so if you think about what are some of the cost alternatives you may face in your life, possibly one of them would be purchasing health insurance. Purchasing the health insurance isn't going to generate a direct yield for you, although indirectly being healthy makes you more productive. But buying the health insurance itself isn't going to get you a cash flow in the future. And so what you have to do is compare alternatives to find out which of them is least costly. You can't have an internal rate of return when the cash flow diagram is negative. And that was introduced in the last class lecture. And the reason why is that the internal rate of return, just by definition, assumes a positive cash flow. So here is a look at the first option we were talking about, which is investment alternatives. Investment alternatives do have a positive future return by virtue of some initial upfront investment in year 0, and then it generates money over time. And so it's an easy case when they both have the same number of years, both the options are going to have the same useful life, and all we have to do is find the present worth of both of these options at the discounting at the minimum acceptable rate of return, and then the one that has the greatest positive present worth or future worth or annual value would be the alternative that is most advantageous for us to select. So here's an illustration of cost alternatives. And in the case of cost alternatives, remember that we're not expecting a positive cash flow. We're expecting there to be an upfront cost and then maybe operating costs over time. In the case of option B here, there's a small salvage value at the end. And so we're not going to be able to calculate the internal rate of return here, but we still can find the present value of these two options. And so here are the numbers. If we find the present value of alternative A, you can see there's the $380,000 investment that's made in year 0. And then you're finding the present value of $38,100, the present value of $39,100, moving it from year 2 to year 1, and so from 2 to year 0, and so on. And so the present worth of alternative A is negative $477,000. Comparing it to option B, where option B is more expensive over time, but it has a smaller annual cost, the operating costs are lower, and it has a salvage value. So the question is option B justified? Is it better to spend a little bit more in year 0 so that you can have lower operating costs over time? Well, when we take a look at it, it is more advantageous. The negative value here of negative $463,000 is more favorable than negative $477,000. You can see that there's the present outlay of $415,000 for the upfront capital costs, and then finding the present value of the annual series and then the salvage value added in. So this is an illustration of cost alternatives, and also this is a great illustration of just what we're going to be doing in chapter 6, where we are comparing alternatives. It gives you an idea of why we have to have these skills, because ordinarily there's more than one piece of equipment or more than one project, and you have to know which one is best. This slide is a discussion of some of the differences that can arise when you're comparing alternatives. And so think about the difference between a bicycle and a scooter. Each of them is going to have a different capacity for output, and so the number of packages that could be delivered in a day is going to be different between the two. In this case, the speed of them is different, and the same, many of these factors is true for any piece of equipment. Different pieces of factory machinery or different pieces of construction machinery or equipment that you use in a lab environment will have different capacity, speed, will have different reliability, where you have to look at the downtime and the cost of repairs. the cost of setting it up and training employees, fuel efficiency. And so you have to really look at the entire life cycle from cradle to grave to have an idea of what the impact of operational performance factors is. Another factor that has to be considered when you're comparing alternatives is what's the quality going to be like from using that piece of equipment. In the case of the circular saw versus a table saw, if you're trying to make furniture with a circular saw and you're cutting up large pieces of plywood, you may not get cuts that are as straight and even with a circular saw as you could with a table saw. And so you may have a higher rejection rate if you're using the cheaper piece of equipment. Think about if you're delivering packages, and if the bicycle has more incidents of the if it's groceries being delivered, the groceries spoiling because it was being delivered too slowly, then that would be another illustration of a quality factor that has to be considered when you're comparing alternatives. And not only does it have to be considered in a sort of a qualitative, soft way, but what we really need to do is we need to find out what are the financial effects of these quality factors and what are the financial effects of operational performance factors. And breaking it down into dollars, how will the revenue and the costs be affected by the differences between the two alternatives? And there's also economic factors that are more directly, more easily and directly able to be compared. And so different pieces of equipment may last, have a different useful life, may have a different upfront capital costs or annual expenses. And the two cars that are pictured here is a Ford Focus compared to a Toyota Prius. The Toyota Prius having a hybrid drive system that has a better fuel efficiency, the Ford Focus being slightly less expensive in upfront initial purchase price, and they may have different useful lives as well. And so economic factors are also wrapped into the analysis of alternatives that we're going to be doing. The bottom line is that in order for us to be objective and find the alternative that is most effective for us, we have to find the economic excuse me, we have to find the economic impact of all of the differences and translating everything into dollars and cents. Now, here are a couple of rules that we apply when we are making comparisons. The study period and the useful life may be the same and they may be different. And let's talk about what each of these are. The study period is the amount of time that we want to be doing a certain activity. So you can think of it maybe as how long a contract is going to be, or how long you'd like a business to be operating, or how long you may have a certain need that has to be fulfilled. Whereas the useful life approaches time from the standpoint of the equipment or the alternative that's going to be selected. And let's take as an example here a 2-year construction project. A building is under construction in this first case, where you can see the study period and the useful life are the same amount of time. And so the study period would be, we need service, in this case cement mixers. We need service, we need the ability to have a cement mixer during the entire 2 years that this building is being constructed. And just by pure luck, it so happens that our anticipated lifespan for both of these alternatives that we're selecting is 2 years. And each of these items is expected to have a usable life of 2 years. And so in the first case, we have a study period that equals the useful life. And that may be rare. It may not always be the case that your equipment is going to last exactly as long as your project. And that's why we also need tools to help us understand the case where the study period does not equal the useful life. In other words, let's say we have a project, in this case a paving project, that we expect is going to last 6 years. That may be paving a series of developments in a residential area over the next 6 years. But what if the contractor who has that project contract has 2 equipment options at their disposal? One option using a piece of used equipment that only has an anticipated lifespan of 3 years, and now a new piece of equipment that could be purchased that has an anticipated lifespan of 6 years. And so now we're going to have tools available that would enable us to compare these two alternatives, these two equipment alternatives, even though one of the alternatives has a lifespan that's less than the project life. And so we've got some strategies that allows us to compare apples and oranges, as you could say, in a way that normalizes and makes the alternative comparison a little bit more justifiable than otherwise would be the case. The fundamental principle that we're going to apply is that we want to use the same period of time for the comparison. In other words, we're going to use the study period for the comparisons, and we'll look for strategies to deal with the fact that sometimes the equipment or the alternative being selected has a lifespan different than the study period. So in case one, where we were saying the study period equaled the useful life, the way that we can select the alternative that's best is simply to use the equivalent worth methods. And by equivalent worth, of course, what I mean is the present worth, annual worth, or future worth. And the procedure is that you find the equivalent worth of each alternative discounted or compounded using the MEAs as the interest rate. So that is, you take the whole cash flow diagram to the present, to the future, or spread out over an annual series using the MEAs, and whichever alternative has the greatest equivalent worth is the one that should be selected. And that's if we are dealing with an investment alternative. Remember, investment alternatives are those alternatives that have a positive cash flow because they're generating revenue over time. Now, if it happens that all of the equivalent worths are less than zero, meaning that we're not able to generate more revenue than costs when discounted at the MEAs, we should do nothing in that case. If it's a cost alternative, meaning that we're forced to do something even when we don't have a revenue being generated, then the cost alternative you'd want to select is the one that has the smallest overall equivalent cost. The item or the project that's least negative is the alternative that should be selected. Now you may be wondering if you'll get different answers if you took everything to the present versus took everything to the future. And the answer is no. You don't have to worry about that. Regardless of which of these three equivalent worth methods you use, you'll always get the same answer on which alternative should be selected. So we've got three alternatives. We've got an alternative that has an annual an upfront capital investment in year 0 of $390,000, and that's going to generate annual savings of $69,000. So we can think of that as a revenue. We can spend $920,000 and then get savings of $167,000 per year, or spend $660,000 and have annual savings of $133,500. Each of these alternatives has a useful life of 10 years, and 10 years is the period that we need to have this equipment in place. And we're going to use 10% as our minimum acceptable rate of return. So if we're going to use the present worth method as our equivalent worth approach, then we would simply have the capital cost already at the present. So you can see alternative A, B, and C each has their capital costs. And then we're going to add to that the increase in revenue due to cost savings, and we're going to find the present value of that annualized annual series, where the MEAs is 10% and we're doing it for 10 years. And so you can see of these three alternatives, the greatest present worth is for alternative C. It has a positive present worth of $160,000. And so even though it doesn't generate as much revenue as alternative B, it's better because alternative B had so much more cost up front than alternative C. And so the present value of alternative C is the greatest, and so this is the option that we'd want to select. Now case 2 is a little bit more complicated. Now this is where the useful life may be different the useful life of the different pieces of equipment may not be the same as the study period, and the useful lives of the alternatives may not be equal to each other. And so one of the approaches that we use to compare the alternatives is to invoke something called the repeatability assumption. And what the repeatability assumption says is, well, when one of the pieces of equipment wears out, just buy another one, and you're assuming that you can get the piece of equipment for the same price as you used originally, and it's going to be generating the same cash flow as it did before. And so if that assumption is true, that you could just replace the equipment once it wears out for the same cost, and that piece of equipment is going to generate the same revenue, then what you can do is just repeat a certain number of cycles of that item. And so let's say that in this case, if it was only going to last for 3 years, then just buy another one at the end of 3 years. And so you'd have 2 of these used items to get you through a 6-year period, and you'd compare that to the cash flow of the new paving equipment that was going to last for 6 years. Now, there's also the case that the repeatability assumption may not be possible. It may not always be possible to get the equipment for the same price the second time around, and it may be that it doesn't generate the same cash flow. And so we also need to have a tool available for what would happen if the repeatability assumption isn't valid and a certain item is going to last less than the study period. Or maybe it could be that the certain item that we're considering is going to have a useful life longer than the study period. So just to begin with, here's an illustration of the repeatability assumption. And it shows that if we had 2 different pieces of equipment, one that lasted for 4 years, one that lasted for 6 years, and each of them has a different initial cost, and each one of them is going to generate a different amount of revenue, then we can compare them by repeating the cash flow diagram over a course of 12 years. And so in this case, we're going to have 2 cycles of item B and 3 cycles of item A. And so you can see here the cash flow diagram is showing that we spend $3,500 to buy option A at year 0, and then we get the revenue. And in year 4, not only are we getting the revenue for that year of operation, but we're having to buy a new piece of equipment so that we can continue through another 4-year cycle. And then we do that one more time. In year 8, we buy another piece of equipment, and it goes on through to year 12. So comparing alternative A, which was repeated 3 times, to alternative B, which was only repeated twice, what we'd want to do is find the present worth about both of those cash flow diagrams. And so that's what we're going to do. We're going to open up Excel and take a look at how we could translate this cash flow diagram into a comparison of alternatives. So we're going to have a certain year, and there's an amount, and then we're going to find the present value of the amount. And we'll do that both for alternative A and for alternative B. And so here is item A, and this is item B. Okay, we have years 0 through 12 that we're going to be doing this. Oh, I skipped a line. All right. Item A has an initial cost of $3,500, and then we get $1,255, and we're always going to get that $1,255 each year, but it's just that in year 4, we also have to buy the item again for $3,500. And so you can see the total cost is negative $22.45, because that's considering both the revenue and the cost in year 4. And then again in year 8, we're also going to have the revenue and then the cost of buying another one. I hope that you'll follow along, yourself, open up Excel and work through this example as I share it with you. The second option that we're going to be looking at, item B, costs $5,000 to begin with, and it's going to be generating $1,480 each year. And so I'll drag that $1,480 down through. But then here you can see in year 6 we have to buy another one of the items, and so we're going to be subtracting the $5,000 again. And now we have the cash flow diagram translated into a table form, but we want to find the present value of these amounts. And in this option we've got a MAR of 10%. That's our minimum attractive rate of return. And so I'm going to do the equals PV function at 10%, so 0.1 is 10%. N is going to be the year that we're in, and then we skip through the payment function. We're going to say it's a future value that we're applying it to. And so it finds, for example, that the 3,500 in year 0 is 3,500 because it's already at the present. And so if I drag that down through, it finds the present worth of each of those amounts, and then I can find the sum of the present worths and find out that this item, this alternative, item A, has a present worth of $1,027.86 if discounted to the present at the MAR. Now, item B, by contrast, I can say equals negative PV. The rate is 10%. N is going to be the year that we're on. And here's the amount. So it likewise takes the amount from the future to the present, and then I want to find the sum of those. And you can see that the better alternative is item B. It generates a better cash flow, $1,480 versus $1,255. It lasts longer. Even though it costs more up front, that added initial investment is more valuable for the two reasons that you only have to go through 2 of the items rather than 3 cycles, because this equipment lasts longer, but also it generates more revenue over time. So we definitely would want to select this item. Select item B because it has the greatest present value. All right, so that is this example of using the repeatability assumption. Now, sometimes it may be that the useful life is greater than the study period. That is, the equipment is going to last longer than some particular contract or project you have in mind. And the most common way of handling that is simply to sell the item at the end of the project. So that if you're going to be buying a tractor for a construction project that's going to last 3 years, but the tractor has an anticipated life of 5 years, you'd simply sell the item and you'd take the money from the sale and include that in the cash flow diagram when comparing alternatives. That assumes that you're able to find a market value for the item at the end of the study period. Now, what if the useful item, the useful life of the item is less than the study period? You know, so comparing just now what we talked about truncation, where you sell the item, that's where the useful life is greater than. Now they're going to consider the fact of what if the useful life of the item is less than the study period under consideration. So we have a couple of different options available. One is that if the item is going to wear out before your study period is over, maybe you could just rent the item after the one that you purchased wore out. And so in the case of the paving contract, you've got a 6-year paving contract and a piece of equipment that's only going to last for 3 years when you buy it used. Well, maybe you could lease the equipment for the remaining 3 years. Another approach to comparing alternatives over the same number of years would be that you could repeat the item and then truncate it. So that is, what if you had a 5-year paving contract and you wanted to find out Well, what would you do with the equipment in the last 3 years? Well, you do 2 cycles of 3 years, and then for the last year that the used equipment isn't worn out, then you could sell it for that last year. And so it's just going to have an enhanced market value because it's not completely worn out at the end of the project. And so that's another approach to how to handle it if the useful life of the item is less than the study period. Another method of comparing these dissimilar items would be to take your cash flow and reinvest it somewhere. Maybe you're going to put it in the bank or put it into a project that generates the MEA, so that you're not doing the project anymore. You're just generating the cash flow and then putting it somewhere else and comparing the 2 different alternatives with different lifespans in that way. And then finally, you could replace the item with something else. So maybe you'd find a paving equipment that lasts for 2 years and another piece of paving equipment lasts for 3. And so the way that you could get through the cycle equal to the study life is just to get the different equipment with their different useful lives. So here's an illustration of how you could do the reinvestment option. So you've got 2 different items available. One of them costs $3,500 and it lasts for 4 years. In fact, this is the item that we were looking at before. When we use the repeatability assumption in the first example that we worked with this cash flow diagram, we did 3 cycles of option A and 2 cycles of option B. Well, if we can't do repeatability, maybe we can do reinvestment. And here, what we're saying is we're going to take the cash flow diagram to year 4. You can find out the total net value of this cash flow diagram at year 4, and then reinvest it during the period from year 4 to year 6 and find out what's the future value of that. And so here's how we'd compare these 2 different alternatives using the reinvestment approach. We're going to find the future worth of option A and the future worth of option B. We want to find what's the value of both of these cash flow diagrams in year 6. And what you'll notice from this solution is that to find the future value of option A, you're going to take the $3,500 from the year 0 to year 4 at 10%, and then you're going to take this annual series to year 4. Here you can see there's the find the future value of some annual series, so F/A at 10% for 4 years. And so now both the upfront cost and the annual series at year 4, and then multiplying it here by the factor to take it from year 4 to year 6. And so the result of that, if you were to look up the factors for both of those, would be to take the amount to the future and the net future value would be $847. And by contrast, alternative B, if you take that to the future, both the cost and the revenue, then it has a future worth of $2,561. And so alternative B is still the best option, even if you're going to be doing the reinvestment of the cash flow diagram. Now we're done with the lecture part of today, and I'd like for us to take a look at the in-class exercise. And this in-class exercise is looking at 2 different machines, machine X and machine Y, and we're going to compare these 2 options to try and find out which one is the most advantageous. In section A, I ask you to use the calculate by hand using the equivalent worth method. That is, the present worth, future worth, or annual worth to find out if the repeatability assumption, which one is best. And in part B, I ask you to, again, by hand, do the calculations if the repeatability assumption does not apply. And so I've got a pencast recording that I'm going to edit into this video that will illustrate how to do that in-class exercise. Before you watch that pencast, I encourage you to try and give it a try on your own. See if you can solve the in-class exercise by hand to see if you get the right thing. In this activity, what we're doing is comparing 2 alternatives. We're comparing machine X, and the characteristics of machine X is that it has a life of 12 years, and machine Y
which has a useful life of 18 years. What we can do is, the common factor between the two of them is 36 years. If we repeat this 3 times, then that gives us 36 years. And if we repeat machine Y 2 times, that gives us 36 years. And from the given table, we can construct a cash flow diagram for each. We're going to have machine X looking like, this is going to take a while because of 36 years is kind of lengthy, but we'll have in year 0 6,000 being spent, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In the 12th year we're going to have to buy another one for 6K, and then have, so this is year 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. In year 24, we buy another one for 6K, and then this new one runs its life. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. We don't buy another one at the end of the 36th year. Now each one of these expenses was $2.5 thousand. For all of those, $2.5 thousand and $2.5 thousand. There is no salvage value for machine X. Now machine Y, on the other hand, if we go through and repeat its cash flow 2 times, we're going to have a diagram that looks like this. In the first year, in year 0, we're going to spend $14,000 to buy the first one, 14K, and then we'll have 18 years of the expenses of this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now in the 18th year, we sell the one that we have had, so it's got a market or salvage value of $2.8 thousand, $2,800, and then we also have to buy another one for $14,000. And then the second piece of equipment begins its life. Year 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So now here we're at 36. It has a salvage value of $2.8 thousand. We don't buy another one, and the expenses were $2.4 thousand in the operating costs. And so you can see how we've done 3 cycles for machine X and 2 cycles for machine Y, and we're both ending at 36 years for those. And so our process is going to be to use the factors in order to find out what is the present worth of both of these cash flow diagrams and compare the present worth. The first thing we're going to do is take a look at the P/A factor. We've got 5% interest and N equals 36. For both of the cash flow diagrams, we're going to want to take the annual operating expenses to the present using this factor. The equation for that is 1 plus I to the N minus 1 divided by I 1 plus I to the N. And in this case we've got 1.05 because the interest rate that's given for this problem is 5%. The N is going to be 36 years minus 1, and then 0.05, 1.05 to the 36th power. Alright? We'll get 4.7918 in the numerator 0.28959 in the denominator, which is 16.5469. The other factors that we're going to need to solve this problem is to find the present value of some future amount at 5%, and we're going to need to do it for 12, 18, 24, and 36, because those all have individual amounts that need to be taken to the present. So first we can do it for n equals 12, and we'll do it later for 18, 24, and 36. The equation for P slash F is simply 1 plus I to the negative n power. So it's going to be 1.05 to the negative n, whatever the case may be. So for n is 12, we're going to have the factor be 0.556837. For n is 18, 1.05 to the negative 18th power. The factor is going to be 0.415521. For 24, 1.05 to the negative 24th power. There we go. 0.310068, and then 36, it will be 1.05 to the negative 36 power, 0.172657. So that helps me to calculate what the present value of all of those future amounts is going to be. Alright, so we have the factors. We can start chugging through the calculations here, starting with machine X. We've got the 6,000 that's already at the present, and it's a cost, so negative 6,000, and then we're going to want to add negative 2,500 times the P slash A factor, which was 16.5469. And that'll take all of the annual operating costs to the present. Then we also have to add the negative 6,000, which is at year 12, and so the factor to discount that to the present will be 0.5568. Then we're going to want to also move the negative 6,000 from year 24. And the factor for year 24 was 0.3101. So that will allow me to calculate the present value of the cash flow for machine X. Machine Y, just to set that up, and then we'll do the calculations for both of them. Machine Y has the negative 14,000 already at the present, and then we're going to want to take the 2,400 is the operating costs, and there's 36 of those. We'll times it by the factor for the P slash A. And we have to take, in year 18, there's the 2.8 thousand that is a salvage value, and the 14,000 cost of buying a new one. So I'll simply find the difference between those. It's 14,000 as a cost and 2,800 as a revenue, and so the net difference is that it's going to be a negative 11,200. That's the salvage minus the new purchase cost. And the factor for year 18 was 0.4155. And finally, now we have to look at year 36, because in year 36 we have the salvage value of 2,800, and we have to move that 2,800 from year 36 to year 0 using the factor. Alright. machine X, this together is going to be negative 41,367.25. The value of this is negative 3341.02. The value of that is negative 1860.41. So the grand total is that this has a present value of negative 52,568.68. So that's the present value of their present worth of all of the expenses. Alright. The present value of that 2400 annual operating and cost for machine Y is negative 39,712.56. For the 11,200 that we're going to be taking as a cost in year 18 to year 0, the cost in year 0 of that is negative 4653.60. And then the salvage value of the equipment in year 36, if we move it all the way back to year 0, is going to be 483.56. And so combining them all together, including the negative 14,000 that was already at the present, then the cost there is negative 57,882.60. And so what that tells us is that the least costly option is machine X, and so we should select machine X. And now here in part B of this example, what we're going to have to do is no repeatability. What we know in part B of this example is that the analysis period is 18 years. And since machine X goes for only 12 years compared to the 18 years of machine Y, we have to find some sort of a substitute in the 6 years between the end of machine X and the end of the project period. And what we know from the description of this example is that a machine can be leased for $8,000 per year after the useful life is over. So let's look at what machine X's cash flow diagram is going to look like. Machine X is going to have its sort of natural cash flow diagram where we spend $6,000 to purchase it, and then we're going to have annual expenses of $2,500 every year to the end of 12 years. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now here in year 12, that's the last year that we're using the actual equipment, and so in year 13 we're going to have to pay $8,000 to lease the substitute. So year 13, 14, 15, 16, 17, 18. I should have made this one longer because the lease cost is $8,000 per year. So our initial outlay of $6,000 to buy the equipment, and then annual expenses of $2,500, and then at the end of year 12 for year 13, 14, 15, 16, 17, and 18, then it's $8,000 a year. By contrast, machine Y just has its natural cash flow. Machine Y is going to look like the original expense of $14,000, and then $2,400 each year. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And it's $2,400. And then it has a salvage value of $2,800 in year 18. So if we look how we're going to do the comparison here, we're going to have find the present value of some annual series where I is still 5% and N is 12, and that will be taking the 2,500 every year from year 1 through 12 back to year 0. And then we're going to need to take the $8,000. It goes 1, 2, 3, 4, 5, 6 times, and so it's going to be a P/A of I is 5%, N equals 6, and so that's going to take it at year 12, and then we're going to need to multiply that is going to be multiplied by find the present of some future amount, because it being in year 12 is in the future and we need to take it to year 0. We'll have interest rate is 5% and N equals 12. The cash flow diagram for machine Y will be a little bit easier. We're going to have to take P/A for interest rate of 5%, N equals 18. That'll take all the operating costs to the present, and then we'll have the salvage value where we want to find the present value of some future amount at I equals 5% and N equals 18. Fortunately, our textbook has these factors available for lookup. The P/A factor is 8.8633. The P/A for N equals 6 is 5.0757, and the P/F for N equals 12 is 0.5568. The P/A for 18 years is 11.6896, and then the P/F for 18 years is 0.4155. Okay, so machine X is going to have the negative 6,000 already at the present, and then we're going to add the negative 2,500. That is going to be times 8.8633, and we're going to then to that add negative 8,000, which is multiplied by 5.0757, which takes it from an annual series and moves it to year 12, and then multiply it by 0.5568, which moves it from year 12 back to year 0. And machine Y is going to have already negative 14,000, and then we're going to combine that with the negative 2,400 times the factor that we have to use there of 11.6896. And finally, there's a positive salvage value of 2,800 that will be moved from year 18 back to year 0, and the factor for that is 0.4155. This amount is negative 22,158.25, and this amount is negative 22,609.20, so that the sum total of all three amounts combined together is negative 50,767.45. This amount is negative 28,055.04, and this is 1,163.40, so that the grand total of this option is negative 40,891.64. In this case, it would be advantageous for us to select machine Y instead of machine X.
Verify using Excel, what we're going to do is translate this cash flow diagram into an Excel solution. Remember, we've got one with the useful life of 12 years and one with the useful life of 18 years. And so let me just start a new sheet here. Alright, so we're going to take a look at years. If the repeatability assumption applies, remember that we're going from 0 to 36. So this is going to be a lengthy cash flow diagram. And here is machine X. And here's machine Y. Alright. And in fact, I'm going to insert another couple of columns so that we can find the amount and the cash flow diagram separately. Okay, so here's the amount, and here's the present value that we're going to do for the comparison. Alright, and so it turns out that we have to spend $6,000 to begin, so our amount is negative $6,000, and then we're going to spend another $2,500 every year through year 36. And we have to spend in year 12, we have to buy the equipment again, so, oops, it should be negative $2,500 since that's an expense every year. Alright. In year 12, we need to not only have our annual operating costs, but also buy another $6,000 item. And we have to do the same thing in year 24. We're going to have that annual operating expense and purchase another $6,000 item. So now, in order to find the present worth, in this illustration we're working with a MAR of 5%. And so here let me have that the MAR is 0.05. Okay, so the present value equals PV equals negative PV because of the strange trick that Excel does of flipping the sign. 5%, I'm anchoring that reference. N is going to be the year, and here is our future value. And I'm going to reformat that to appear as currency. And I can carry that through, and then I can find the sum. And so that's equals sum for the formula. And the sum of the cash flow diagram, there's a negative 52,568. And that matches right up with the calculations that were done by hand now that we're verifying it with Excel. So that's always a good sign. Here, this cash flow diagram is that we need to spend in year 0, negative 14,000. And machine Y has an annual operating expense of negative 2,400. And so I'm going to carry that through all of the years of interest. But remember, we need to purchase the item again in year 18. Year 18 is a little bit more complicated because not only do we have to buy the equipment again for $14,000, but we get the salvage value of $2,800 for the old item that we're selling. And so remember, here it says that there's a salvage value of $2,800 for machine Y. And so then here in our last year, we're going to have the $2,400 operating costs and the salvage value of $2,800, but we're not buying another one because we're done with the project. So we'll do the equals PV equals negative PV with our rate being the MAR, the year is the N, and here's the amount that's being moved from the future to the present. I'll reformat it to appear as currency and carry that formula through. Oh, did I not anchor the rate? There we go. And carry it through. And then I'm going to find the sum of all of those present values. And the sum of the present values is negative 57,882, and that's what we got with the paper solution as well. So the cheaper alternative is this one, and so we should select machine X. It's the alternative that's most favorable for this cash flow diagram. And that was assuming the repeatability assumption applies. Now we'd like to verify part B, assuming that we're going to lease the equipment for $8,000 a year after the useful life is over. And so we're going to do machine Y for its natural length of time, but then machine X, when machine X has to be retired, we're going to just lease the equipment for $8,000 a year after that. So starting from scratch, we've got year, we've got machine X, and machine Y, and the original amount that's listed and the present value of amount. Let me put in another column here just so I can separate. I can just separate the two. Amount, the present value of the amount, move that there, and then we'll do the same thing for machine Y. So our cash flow diagram is going to go through 18 years this time. All right, and then the amounts are going to be the same as before. We've got the cycle here. Let me paste this over here. So it's that same amount, except for year 12 is going to be another negative 2,500. You'll remember that in the previous one, here I was doing the negative 8,500 because I was not only having my operating expenses for year 12, but I was also buying a new item. I'm not going to buy that item again. And so after the equipment wears out, it tells us in the in-class exercise that we can lease the item for $8,000 a year. And so I'm just going to spend $8,000 a year to lease a new one. Let's see here. All right. So now negative $8,000. And I'm going to do that through year 18. And so at 5%, I'm going to find the present value of equals of everything. At 5%, here's my N, and here's the amount in the future I'm taking to the present. And then I'll take the sum of all of those. Negative 50,768. And that's exactly what we got when we were working on paper, which is good. And machine Y, we're going to just take its natural life here. Except for that, I'm not going to buy another one in the last year. All right. So that's machine Y. And I'll do the same present value formula at 5%. Here's N. And there's the future value. Okay, I put in too many parentheses. There we go. Reformat that as currency. And find the sum of the present values. And so you can see that this option machine Y, is better because it's the one that has the lowest cash flow costs. So it's better for us to, if the repeatability assumption applies in In this illustration where we did the repeatability assumption, machine X was better, but if we can't repeat and we're forced to lease the item for $8,000 a year, then in that case, machine Y would be the better alternative.